Well, I think I'll go ahead and start. Good afternoon, everyone. Thank you for coming to this Alumni Award lecture by Professor Tara Javidi. I want to say a few words about this award. This is a officially called ECE Alumni Distinguished Educator Award. This is an award that ECE gives to its alumni, and it's the highest recognition to our alumni in academia. It recognizes alumni who have made a significant and lasting impact in education. The awardees are regarded as visionaries within the field and are celebrated for their exceptional work in educating the engineers of the future. And with that, let me say a few words about Tara. She graduated with a PhD degree from the EECS department, working with Professor Dimos Tenaketsis in 2002. She joined University of Washington, Seattle, was there for a couple of years, and then she moved to UC San Diego, where she is now. She is the faculty co-founder and founding co-director, as you can see, of the Center for Machine Intelligence, Computing and Security. She is also the co-PI of this newly funded NSF AI Institute for Learning-Enabled Optimization at Scale. Congratulations on that. Her research interests are in the theory of active learning, statistical inference, information theory with feedback, stochastic control, wireless communication, communication networks. Among her many awards and recognitions, I'll mention a few. She's a fellow of IEEE. She's a recipient of the NSF Career Award. Back when she was in Michigan, she also received the Barber Graduate Fellowship. She is a Qualcomm faculty awardee for 2 years, 2018 and 2019. And most recently, she and her PhD student received a 2021 IEEE Communication Society and Information Theory Society Joint Paper Award. So she is a very accomplished scholar and educator. Let me end this by saying a few things about my personal experience. So I've known Tara for as long as I've known anybody here, probably longer than all of you here. She came to my interview dinner when I interviewed in Michigan in April 2000. So yes, we go back a long way. She is a good friend and a colleague. So with that, we're delighted to have you back here, Tara.
Thank you so much. Thank you, Mingyan. That was such a nice introduction. I'm really humbled, especially around everybody in this audience. It's humbling. It was very generous. So I'm going to talk about some work that I've been doing in the past, I want to say 10 years. I'm going to apologize because I wasn't sure how to calibrate the talk. So the talk is fairly high level. So if folks are interested and want to challenge me, we can go deeper. But really, I was thinking maybe something that would motivate students to think about really how the kind of educations I received at Michigan in systems and decision theory really can be applied as we move forward, especially with data science and machine learning. And because it's 10 years of work, I have many PhD students who have worked on many of these topics, have color-coded them, and also brilliant collaborators that you're seeing. So let me get started. So I'm going to argue that first two generations, however way you want to describe the generations of data analytics and machine learning, has more or less ignored how data has been collected. So the data is there, and you are often tasked to infer something about a hidden parameter or learn a model that describes the data. But the data is practically given to you, passively collected often. And for example, if you're thinking about supervised learning, it's data that has been labeled by labelers, sort of before you start analyzing the data. And inferences are done on arbitrary data. You have almost no control of which data you're looking at or which data you're trying to infer something on. And when I started thinking about this problem from engineering background that we all are sort of thinking about, in many practical engineering applications, you have a lot of control over the data collection process. So whether you are managing your sensors and the data that you're collecting for inferring in runtime what things are going, or whether you're collecting the data that you need to even label. So my favorite example on the runtime is all of us are familiar with, like, if you want to sort of do a surveillance of an area, you can fly a drone, and we all know that depending on the elevation, you will get very different kind of images. And so that's where I think controlling the sensing in the runtime will come up. And this is the kind of, and these are images that my students have collected. This is the same field. This is from fairly close to the ground, 16 feet. 16, no, not 16 feet. Yeah, something like that. And the other one is 4 times higher. So you can see that the area that I can see is far larger when I'm flying higher, but the quality of the image is fairly poor. And these are the sort of drones that my students nowadays buy. They're cheap, $150, $200 drones. And the question is, which one of these information you want to collect for the kind of task that you have? In the data collection process, you can sort of think about the same thing. So this is a flowchart for an active learner. So we're all familiar with supervised learning. You have data that is collected on cats and dogs, and you want to find a model that explains your data fairly well. Now, cats and dogs are fairly cheap objects to get labels on. Imagine if you want to do this for medical diagnosis application. So now you have tumors that are labeled as, benign or not. And now you don't know, the time of a doctor is very sensitive and very expensive. So you don't want to go to the doctor and show them the same amount of information. So you want to be stingy about which data you even collect, right? So that's the same phenomenon that we're seeing. So in that sense, the idea is now I have these new systems, and I want to really try to optimize the notion of information. And this question was what we posed maybe, as I said, 10 years ago, said, can we actually say something kind of interesting about this problem? And then how do we deviate from the classical way that people are thinking about it? So, and if you, for those of you who know and work in any depth with demos, if you work with demos, you're always afraid that you will give a talk and you say, I have some new result, and somebody in the back would raise their hand and say, this was done in 1930s. So what I want to do is do a brief history of people who have worked on this problem and show you that this is actually a fairly known problem and was studied long ago. So the problem, again, I'm vague on the specific description, but the idea is I have an unknown parameter or maybe a hidden variable or hidden state, and I would like to track it by collecting controllable data collection through partial and noisy observations, right? And in this sequence of observation, I can collect and sort of decide on what that parameter is. So you can sort of think about it in the easiest case is if you want to estimate that parameter directly, or in harder case, you want to use that parameter for something like a control setting or what. And what I'm going to talk about is the work of these 4 sort of visionaries, since this is a talk to celebrate educators being visionary. And I think the work really shows that the sort of conceptually people way ahead could think of the same problems. Computationally, how much they made progress on it was, of course, limited. So let's start. So the first, and of course, again, to just remind you, in the active learning setup, the data collection is done for learning a model. And in the sort of runtime inference setup, I have a state. Let's say the ball is moving on this basketball court, and you would like to track it. But really, the flavor of the problem is the same. And in fact, the first version of this problem that I could find is due to two independent yet parallel work of David Blackwell and Stein, by themselves visionaries. And in 1952, they formed this single-shot version of this problem they called experiment design. And they basically looked at one experiment, A. This is what I'm going to call action, so hence the name A that I picked. So they talk about experiment A, and they say if you give a single experiment A, I would like to use these experiments to disambiguate and mutually exclusive hypotheses. Think about it as medical experiments, right? So you would like to know the state of the health of a patient, and you have mutually exclusive diseases or conditions that they might have, and you want to sort of think about an experiment that you would design to distinguish these health conditions. Now, the challenge is the test that you will do will result in noisy and partial observations. And in their work, they assume that the likelihood of what they will observe, if they decide on experiment A and the true state of the health of the patient is I, these likelihoods are given. So these are the models that they assumed on this. And they asked this question of what should A be? Or in particular, they said, can I compare two experiments, A and A prime? How can I order them? Is there a way that you can say one experiment is more informative or more useful than the other? Unfortunately, the results is rather limited. They showed that if one experiment results in an observation that is a pure stochastic degradation of another experiment, you can throw away that experiment away. Even though the results are very intuitive, it's very powerful in the sense that I said it really didn't matter what the experiments are, what the task is. This general result holds for a variety. So, it's good to sort of try to understand how simple their arguments were, because it gives us. So if I put a Bayesian view of this problem, so meaning for every hypothesis I assign a probability rho I. So now I have a probability profile on all of these mutually exclusive hypotheses. And given this prior, or this probability that I put on my hypotheses, I can imagine the distribution of my observation under experiment A. It will just be a mixture distribution that mixes those likelihoods with these certain probabilities. Right? So if I assume I know nothing, they're all equally probable, it's just going to be average of those observations, the mixture of those observations. So you can do this fictitious game in your head that, of course, I will collect an observation. It will be a sample with this distribution. But after I have seen it, I can run the Bayes rule and sort of compute a posterior. So it's just the basic step in this idea is this Bayes rule, right? Sorry, I was trying to make it more legible. So the bottom line of their paper is to understand how Bayes rule under one experiment compares to Bayes rule under another experiment. And that's why the result is very general for any likelihood and any family of actions and experiments it will hold, but it's limited because if you work with Bayes rule, it's hard really it's nonlinear, it has all these difficulties. So that's where they stopped. Then their academic brother, Chernoff, a year later, published a paper that I think to this day sort of has provided a sort of a large path of research in statistics literature, where he looked at an asymptotic version of the problem instead of single shot. He looked at many, many shots. In fact, he sent the number of steps to infinity. So this is a typical world of these visionaries. They would envision a really interesting problem, they could only solve really simple cases. One is just one shot of the problem, and the other one is infinite shots of the problem. So the setup is exactly the same, except for now I'm orchestrating a sequence of observation. In fact, infinitely many of these, such that my error probability of estimating it incorrectly will go to 0. So you sort of think about this generalization. And so many people have, and he identified what would be the fastest way you can kill the error probability. And that became sort of the gold standard. So if you give me a hypothesis testing, what is the fastest way? So it's a fairly nice extension of hypothesis testing where the error probabilities characterization was well understood. So he could show that this actually, how to optimize that exponent. And so the bottom line is, as the number of samples grew, the noise can be averaged out. So you basically have a bunch of distributions. And if these distributions are separable in a statistical sense, you can distinguish a Gaussian versus a Gaussian with a different mean. That's where the sort of dominating factor in how fast the error probability drops. So this is sort of the general flavor of it, if I don't want to get too deep in the mathematics. Now, what really interested me is that when you look at the practical folks, what they do when they're dealing with these problems, and I showed you one example. My favorite example is this flying drone looking for a object in a field, or there are other examples I will talk about. You get a very different, what the practitioners do is very different from what Chernoff would suggest. So this sort of trying to optimize this exponent ends up giving very different results. And the solution that people in practice use is really motivated by 10 years later work by de Groot, another very well-known decision theory statistician, who looked at measure of uncertainty. So he said, if I can measure uncertainty of my priors, then all I have to worry about is compare the uncertainty in my prior with my uncertainty in the posterior. And of course, because posteriors will be different depending on what you've seen, then you have to expect, you have to average with respect to all of that. So that was his motivation. He said, the best experiment is one that maximizes this. And he called it information utility. Now, one would argue that this is very, very much influenced by Shannon and his view of measuring uncertainty. And again, I apologize to all of those who know. For students in the audience, notion of uncertainty has to be defined such that if you have a sort of a probability profile like this, it will give you a small number. This is a lower uncertainty, and this is higher uncertainty. So there are well-known notions of uncertainty, in particular Shannon entropy, that one would be able to compute these. But in general, his results are, again, independent of what that notion of uncertainty is. So define it for the problem at hand. And in fact, because he's looking at this decision theoretic version, you can then say this measure of uncertainty is the optimal value function in a certain fixed point. And as I said, I was sort of struggling to understand whose vision really I should have in mind. As I said, the practitioners often do something very different than theoreticians. So theoreticians who are sort of following Chernoff, they would say, I want my separation of these distributions to be maximized. So if they have to search a field, a large field, looking for a basketball, they will fly the drone as low as possible, because that's where your information is most distinguishable in terms of statistically from any other. So they will say, go get really low and fly really low and scan through the whole region. That, in fact, can be shown if you put a simplistic, a caricature model on kernel of observation, or even maybe a more realistic, like deep neural net to do these. You can show that indeed these are asymptotic optimal in the context of Chernoff. However, most practitioners do not like that. I think all of us have intuition that you want to fly up. Parts of this is kind of empty. You don't want to bother. You want to sort of focus on areas that seem potentially to have the target and sort of come down and search for those, right? Binary search, right? So most practitioners sort of do this. And in fact, there's a name in the literature of folks that do this in robotics. They call it infomax. They maximize mutual information just doing this. And they pick this. And so the first question we had, what should we do? What is the difference? Why is this such a big gap between the two pieces of literature? OK, so I can talk a little bit about the theoretical insights that motivated our work, and then give you examples. So this is work that I did with Mohammad Naqshvar. The first version of the work came out in 2013 in Annals of Stat, but we have sort of built on that quite further and further. And one thing that we noticed that was missing in Chernoff's view of the problem is a fundamental trade-off between performance measures. So you could have a performance measure that says, I have to do this job with very large complexity versus with very high reliability. So let's look at the examples I had in mind. So I can give you this field and tell you, just give me the quadrant that the basketball is in, but please be really, really sure which quadrant, right? So there is this question. Or I could break it into smaller bins, quantize it far more. The complexity of finding the ball becomes harder. The reliability, the question is, how do these things work? Of course, I sort of waved my hand that there's resources and costs, right? So if you have good cameras, the complexity scales better. If you have a lot of power to fly and you can wait a lot, you will do better, right? So for any given constraint on resources and cost, you can sort of think about it. What is the best complexity and what is the best reliability? And what our work showed is that you cannot have both of those performances be optimized at the same time. So there is a natural trade-off between complexity and reliability. So if you want a setup where, somehow, I don't know. So if you have a setup like that where your complexity doesn't grow, the complexity is fine, you can really get really good performance in terms of reliability, and Chernoff will give you a good response because it would just say, among these regions, find the ones that are most distinguished, find the best strategy to distinguish them. It does really poorly here because it has to search every single, basically, corner of the field, and it will do very badly. It has to scale. So this was the flavor of the results. So there's a fundamental limit. And in fact, the analysis is very much like the Shannon theoretic analysis of rate reliability for communication over a noisy channel. So that was something that in the stat literature, people had not really thought about rate with which you're actually looking, or the timing. And this was because Chernoff looked at infinitely long samples for M hypotheses. And this is like log M bits, infinite time. Of course, you can kill error probability to 0. That's what people in channel coding, you could do it even with sort of repetition codes. But it's not a good code if you want get rate. And I guess now in this audience, everybody must know Shannon, right? So I had a quiz. Everybody knows the statue in front. So this is a much, much more impactful alumni, I would say. So the only reason that I put this up is just a little bit of a cheap advertisement for Information Theory Society. So there is a great documentary that we funded. It's called The Bit Player. was done by Mark Levinson, who is a documentary filmmaker, a science documentary filmmaker. So if you haven't seen it, you can. Yes. That was the one of the right before the thing. What is the complaint? Included. So yeah, the selection. I have a same complaint because they interviewed me too. No, I'm just kidding. But they interviewed a whole lot. Yeah, Mark chose whoever chose. But I think the net result is good for students and so on. Yeah, it's like there is no other. Yeah, it's true. It's true. And in fact, my postdoc, Anand Sarwate, has this big ending to the like if you just watch the video. So I have many conflict of interest for advertising with this one. One of them is that. So the nice thing about these results, and that this is the continuation that we have had since Mohammed has graduated, has been that this analysis allowed us to provide a best case scenario for open loop solutions. Because you might ask yourself, I have been saying you look at what has happened, you write Bayes' rule, all these computation, and you keep changing. If you don't want to do that, if you want to just do an open loop solution, what would the best open loop solution do? So first of all, this gave a really nice connection to classic information theory with coding, with open loop codes, and in fact gives us a bound as how passive systems will do. And now you ask yourself, what is the best you can do with active? And there, we just used our own algorithm, but the field is wide open. So our algorithm did better than the best converse that you could get for the passive solutions. So, and the funny thing is that gap, the value of adaptivity, scales quite drastically with SNR. So in high SNR regimes, you actually gain nothing in an asymptotic sense if you do this active orchestration of sensing. But when you go to lower and lower SNRs where noise is dominant, then you really are bound to think about these adaptive schemes. Okay, so let me just talk a little bit about the specific examples. And again, I'm going to talk about the dynamic flight optimization for search and tracking. By the way, there was, at the time when we started this work, there was a challenge that, basically you're tracking, use the drones to look at sort of floating glaciers and things like that, computer vision, purely computer vision. And the performance here, the metrics of that are used is the area of the search. So the larger this area is, the complexity is harder, how reliable you want your decision or the accuracy, and how much time you have. So this is not just an arbitrary sort of notion of search time. This is something to do with the dynamics of things moving, right? If something is moving fast, you don't have a whole lot of search time to look for them without their location to change. And the resources, as I talked about, is quality of camera, number of sensors on board, elevation restrictions, and so on and so forth, right? So we started looking at this problem. And really here, the common, the easy sort of way out in terms of connecting it to the problem that I was saying is this very simple. All computer vision-based classifiers that we have looked at, they fail when you fly really high. They don't have the sort of the feature extraction at different scales of images. So flying close, inherently inefficient because you have to basically scan the area linearly with the complexity. Flying high, you have a lot of error. So now you would like to optimize this. So this is sort of the same image that I have talked about. So, and I like to think about this is like really finding a needle in the haystack, right? Like, so you have like something really small, the larger the haystack, and the more complexity you have, the harder it is. Now, the funny thing is that this is the paper that Mingyan was talking about on the Joint Best Paper Award is applying the same exact techniques that we use for flight optimization for aligning sort of millimeter wave communication. So this is the setup when you have millimeter wave antenna arrays at two ends. And because path loss is terrible at these high frequency, you want really narrow beams to sort of align the communication and defeat the path loss. But if the beams are very narrow, you constantly lose each other. So for example, for AR/VR, just by moving my head is enough to lose connection. So in these scenarios, you have this really sort of a high complexity, high resolution search of where the transmitter is transmitting or where the receiver is listening to. Similar problems that Qing Zhao at Cornell has shown happens when you do sort of looking for attackers in networks. You have lots of sort of traffic coming through, so you can look at the IP addresses and sort of sift through, and there are few people who are misbehaving. How can you actually look at this? So again, there are few misbehaved people. If you look at IP description at the higher layer, higher levels, you are collecting a lot of data, so you might miss those few bad apples, and so on and so forth. So the setup of the problem is the same. So here, in terms of theoretical results, we could see that there are two benefits in looking at this problem from the perspective of hypothesis testing or active information. One is the hierarchical representation, meaning if I allow the drone to go up and down, I have this hierarchical structure of information that I can use to then do inference more efficiently. And the second, as I said, was how much do I gain now that I'm doing this going up and down? If I do it randomly, open loop without seeing the observation, I gain something. Can I do this random operation and be as good as adaptive? So we showed in the first part that this hierarchical structure is better than just do a waypoint, a fixed waypoint at a fixed elevation. And then we showed that, in fact, if you on the fly change your strategy because of what you're seeing, then you can be even better off. So there are sort of a two steps of analysis. Let me see how much time I have. Okay, I'm not bad. So in practice, this is my sort of wake-up call after being Demos's student. In theory, there is no difference between theory and practice, and in practice there is. So my story is that a student came to me before we started this work on drones, and he said he wants to do computer vision, and he has seen me give talks on active hypothesis testing, and I always have images as my example. So do I think that my theory will be applicable there? And if you have studied with Demos, you think you can do it because you're a theoretician. So as I said, sure, of course, it's easy. We'll figure it out. And so this was, as you can imagine, took me a humbling path to see where the theory actually can really play a role. So I just want to show you what we did. So this is in my lab now. I have quite a few number of these sort of off-the-shelf drones. They are built by, these ones are called Parrot Bebop. They're actually not being built anymore. But there's this Parrot company. They build off-the-shelf drones. And that means that you get like some sort of SDKs to control the drones. And the goal was, and what I'm going to show you, the goal was to find that basketball finally in this court. And the setup is, kind of going back to the theory part, was to really try to do everything that I've said with these, simple models of noisy observation and so on. We replaced all of that with modern day computer vision techniques. So the drone basically, this is the brain that is on the phone, and the drone takes images and uses the state-of-the-art convolutional neural net to make decisions about where where to go. And this is the part that we contributed in because of our sort of theoretical bringing, that you should put some belief about where objects are and use sort of lightweight compute to sort of compute these beliefs. And then as you go lower and lower, you can do more and more sophisticated vision tasks. And sort of we wrote this, and so this is and again, it was a really humbling experience, because when I started, I thought, oh, this will take a week. I mean, come on, how bad this is. And this is actually the video that I have to show, just because I feel like I've learned everything from Demos, but this I have definitely not learned from Demos. I've learned from my students. So this is the drone going up and down, and this is what you sort of see on the screen, and it tries to say, well, I couldn't find the basketball, but it sort of looks at some sort of a belief and say, oh, what should be my next movement too? So you can see it says go down, and so it just basically goes up and down, find real time on the phone and communicate it to the drone. Unfortunately, these drones don't allow, or maybe fortunately, these drones don't allow you to do a lot of compute on board, because it makes their systems unstable. So they pass everything and you just run it on the phone. So you have to optimize the neural nets, for example. They're running on the crash. So it will just sit next to the table to prove that we are a theory group. Yes? Yes, so we train them. So we use the training that was done in general, but what happened is at very high elevation, all of those trained models that we could get off any best practice were not good enough, because they would not give us anything. So we had to train a very lightweight, almost like a one-layer neural net, to just be, we called it a zoom indicator. Is this information suggest that there is benefit in zooming in? Right.
So what do you use to train? What kind of data? Are they actually pictures?
Actually, it is from the flying here. So you're basically doing a bit of a reinforcement learning. From the past experience, you're actually learning a model there. Yeah, so it's both active learning and active inference, but yeah. And what we learned, actually, it was very funny, is that the color of the day, like if it's sunny versus if it's cloudy, it completely changes the neural net's performance, right? Because most of the internet images of basketball is like really orange, so it's like that part like played a role. And if you saw the images that I showed, when it's like a cloudy day, the basketball doesn't look like the orange object. So.
In order to run a successful demo, which happens in the DudaStack Center, you have to assemble your system in
there. Yes, absolutely. Changes, yeah. So that's what we did. So instead of doing that, we had we had a running parameter that was sort of determining what day today is, so which model to use, and so on and so on. So that's why I'm saying it really humbled us, because the theory is easy. It's just you estimate some model, but it turned out the models are very different. There was another thing that I had not thought about, which is in my theoretical world, going up the tree, down the tree, doesn't matter. You're just taking samples. Now, if you have a drone and it's going up, it has a lot more cost than it's going down. So all of these things we had to really change. So it was not as cheap to make it. So our algorithm, both for example, antenna alignment as well as this, it sort of starts with a large area and it zooms in, and it accepts the fact that you might zoom in by mistake to an area that doesn't have your object. So the idea is you zoom in and out depending on what you have seen. Now here, zooming out was very expensive, so we had to be a lot more conservative than the original algorithm had asked. And as I said, there is some benefit of putting a partially observable MDP type on top of it to help with this. With all of this. Oops, sorry. So as I said, you can take the same idea and do the same for the millimeter wave, and there the story is very good for theoretician because the path loss is so bad. We are really, really looking at low SNRs, and if you don't do adaptive processing, it's hopeless. It was before us, nobody had any operationally useful version of millimeter wave where you're using standalone solutions of millimeter wave because they couldn't line it up. So they would do omnidirectional on a lower frequency to find each other, lock in, and then just like never move. Or if you're moving, it's a very predictable movement. So if you ask people who are doing demos and say, is this really a movement, God, swear to God movement, they would tell you no. So that's sort of the good news there. So, okay, I have 10 minutes. Yeah, so let me just tell you about active learning. The story in active learning is sort of interesting. As I said, this is, we are looking at sort of classification with supervised data. So the classic approach is passive learning. You have cats and dogs, and you get the labels, so you get all of your data, ask a labeler to label it. Hopefully the labeler is not drunk and is not, malicious, and you get this clean data, and then you learn it, sort of the best classifier. Here I'm showing you sort of linear classifiers, just they look easier. The problem is when you look at passive learning, you have a lot of redundant labels for this to work. So you get a lot of data that already you knew that there's a cat or dog that your labeler has wasted time. In active learning, and I should have really been smarter about pictures, as I said, medical diagnosis is the best example. Your labelers are not cheap, so you go back and forth and really try to get data labeled that is the most informative about what you want to do. So you want to learn this classifier, but far fewer data to actually learn this classifier. So active learning has been used in this context. We had looked at the Bayesian version of it, other groups as well. And we have seen that this is actually beneficial in terms of query complexity or sample complexity. But what we were interested in the work that I did with Kamalika Chowdhury was, can we use active learning for other aspects? So one is, what if data is imperfect? Right? The data has noise. So this is something that is like unclean data or dirty data. This is something that, again, when you look at the problem from this hypothesis noisy observation perspective, you feel like I can really deal with that because this is noise averaging. And then the second one was learning from logged data. So this is becoming kind of common that you find a data set that people have collected for a reason. For example, on medical diagnosis, you have data set on the efficacy of a certain drug. Now, they have not given this drug to a population randomly. There is no really controlled experiment. This is the data that this particular doctor has given this particular drug under some sometimes known, sometimes unknown rule to their patient. And the question is, can I actually use this log data and really learn something? Can I actually actively collect data that is information that is missing? So that's the results that we had. So as I said, we showed that you can learn from imperfect labelers. So labelers that make fundamental mistakes, you can smooth out by averaging their behavior. But then more interesting, labelers that are not sure. So they're careful, but they give a lot of I don't know because they don't know what to do this. We could show that, in fact, in their hesitancy, there is information about what classifier would do. So their hesitancy is actually. So we have an adaptive algorithm that tries to learn from these imperfect labelers, and if there is a consistent behavior that makes the sort of classification easier or harder correlated to what the labeler's decisions and imperfections is, it can actually exploit that. The second, as I said, is sort of sample selection bias. So you have data on images off the internet, and you learn, okay, how to determine sort of like a antenna tower versus a tree. But these images are sort of collected off of a website with biased data. In reality, you fly your drone, and now this is the data you're seeing. And we showed that you can use counterfactual arguments to actually start from an image like this, fly kind of like, in sort of ways that are complementary from a vantage point to the data that you're missing. So you can then, again, complete your data set in a much more effective way. OK, so last piece, I guess this is for these crowds, is the part that is, I'm what do you call it? I am preaching to the choir. So where does the EE and system theory perspective come? So even though the problems really that we're looking are very relevant problems to data science and, machine learning at hand, I think what we have learned viewing it from a decision theoretic and system theoretic view is very useful. So in this set of work that I talked about, a system view was really what initialized our research. Data from engineering perspective is never free, and it's never arbitrary. Data is always collected with some effort, and you design sensors for certain kind of information. So that was the first step. Of course, stochastic control theory was basically all of this. Can I actually adapt my measurements to what I'm looking? And of course, information theory, fundamental learning, fundamental limits on how much you can learn. That's a very particular way of formulating these problems. And of course, this sort of estimation theory aspect of this. And finally, this is going back to what Mingyan was asking, this complementary role of data and models. So I feel like in a lot of the examples that we have worked, some that I showed, and some that I have worked, in different contexts, there's this sort of data and model. And I have learned that this simple feedback model of there is an observation, I need an observer to sort of disambiguate this, and I have a controller to decide where to go. These sort of separation principles have really helped us think about architectures of neural nets. So even though I have replaced all my decision making from this nice linear models to these complicated data-driven models, the architecture have been very much driven by what the theory, simple caricature models have given us. And then you start from that analytic solution. It fails miserably, and then you just keep iterating on it until you find the right one. And I should say, I have told my students, so the computer vision project, we got it NSF funding to do this work before deep learning came out. So this was funded in 2012 or 2013, I don't remember. But by next year, deep learning was like doing everything vision people were. And I had a vision co-PI, Lana, who told my student, go do some theory. There's really nothing you can do here. And what I told my students, like, oh, no. Go find a theoretical problem that you can do order-wise better than what practitioners are doing. So, for example, for this drone one, really the practitioners were looking at basically searching looking at all boxes, trying to, and this grows polynomially with the complexity of your region. And if you're thinking about flying higher and lower, it grows logarithmic. Did we get the logarithmic? Not really, when it was very expensive to actually do that. But that was a really guiding principle that even though we lacked all the intuition as how to hack the models, the gap was so large that it really helped us. So that really helped us think about this. And then this idea of counterfactuals. We learn a model, you kind of work with it, and it's been really important in getting some of these things. OK, so in conclusion, summary, I should say, I have been sort of obsessing over information acquisition in machine learning applications. So almost all the hard problems that I hear, I try to ask the simpler question of, is it easy to acquire information? And then I'll think about control and those parts. And there, sort of the fundamental idea is this notion of information rate. Can I actually do this in a way that scales? And this sort of achieving this optimality. Applications are everywhere. I didn't talk about all of them, but this is a fun project. Almost anything these days you do, you have a control over the data. One thing that I didn't talk about is all of this stuff I showed you, you had one computation center and you were sequentially designing things. When you have multiple drones, for example, with the task of tracking objects in a field, how do you balance the parallelism versus the sequentiality? This is a really interesting topic. I know at least 6 or 7 of you who are working on this problem. And then sort of this doing it in a federated and a decentralized way is really the key there. And with that, I guess I'll just stop. I hope I didn't.
I'm not an expert.
So the remote.
Yes. So the question is, when you do neural network and, machine learning, has there been any study that you would find out that with this training data set that I have, what is the outcome in terms of accuracy of what the machine would predict? Is the dimensionality of the training data set affects, of course, the performance of the machine. Mm-hmm. But has anybody quantified that? How much training do I need to get to 2% error?
So that's a great question. So these days, machine learning is like a big, there's, if you're talking about a deep neural net with like 10 layers, I would argue there has been some attempts. So people, for example, one thing they do is they don't start with one model. They put a sort of a probability distribution on the models. And then they kind of learn on these samples. So you try to sort of estimate the weights with some variability, some variance built into it. And now this variance kind of feeds forward, and you can get some notion of variability on what you're predicting, right? So there has been some attempts like this to do that. In practical world, where it's really successful in terms of practice, we haven't seen those to carry over as successfully. In the models, there are some really interesting work with linear models and such, where people have tried to add confidence intervals to the parameters and sort of carried them forward. That is really interesting. But you're for sure on the spot that the next questions are reliability, explainability, which features right now, if I change, they'll play a most critical role in. And in what you're seeing, we have had to do that, right? Some of this work has been trying to estimate which weights are important, especially in the decentralized way. So there's this work we have done on federated learning. So I have a data that I'm training a model on. You have a similar data, but it's, the simplest is keyboard. We're both typing and we're learning prediction rules, right? So there's been interesting work on take a model from me, take your model, average them, and this is better. And then what is very well known in this literature is if your data is on one set of, let's say you're making a sort of a keyboard English estimation, and I'm doing an audio version of it. So our data is different modality. Then it's meaningless to take your model and my model and average them out, right? But if you take these sort of Bayesian views or these probabilistic views, then you can start thinking about, now that's a part of the model I know nothing about. So these are features that I'm going to be on, I don't know anything. And so you can work on the averaging of the beliefs rather than the models themselves. And that has been quite interesting and something that has, computationally, how much we can scale it has been always the bottleneck for my group, really getting the computations controlled.
Other questions?
So in all your examples of videos, you have the ball static, right? No, but if the ball was evasive, as if the ball didn't want to be found, or the ball would just arbitrarily jump, what happens?
Yeah, so in the case of ball, we didn't do it. That was hard enough to get these drones permission to fly, things that are nothing technical. But in the millimeter wave, we have looked at that. So we assume that the other end, there is somebody who is mobile. And this is where we have learned the most interesting aspect. So if I have a model of their movement, you can build it into your zooming in, zooming out. And in fact, you can easily say, I can zoom out and learn something about where they are, or I can zoom in, and by losing them, I learn something about their mobility. So you can easily do this sort of mutual information trade-offs between different variables, between the models of the mobility and not. And so we have some nice results. The theory, unfortunately, unlike the static case where I can define information theoretically, as you all know, information theory is terrible with, sort of a source that is moving, right? So this would be equivalent of a joint source channel coding. With Andrea, we have some results as what you can get in terms of guarantees, but it's by no means as clean and nice in terms of upper and lower bounds. But algorithmically, it performs really nicely because you can just do this. And then that's where we have deviated very much from the work of other people who have done this alignment, like Wei Yu, Elza, and others, who are great friends, that they have really trained a neural net to do reinforcement learning on the directions. Because they're learning all the physics in addition to your mobility. We have said, the physics I understand more or less. The first order characteristic is if you're there and the path, not you're there, if your dominant path is in my beam, I know what I'm getting. So I'm going to use that physics part and then our neural nets are all about learning your mobility. So that has helped us to do quite well because we don't have to learn, our data doesn't have to learn the laws of physics that we assume we know, and it's worked fine for us. So that's a really good question. But theoretically, what kind of guarantees do you give? I started with very ambitious. We have some results at the beginning with Yoni Caspi that I wanted to say, if you move really fast and the noise is very high, there's just no hope that I can track you below a resolution, right? I don't have any. That would be Demos's 1970 paper on joint source channel coding with dynamic.
More question?
So for the basketball tracking question, so I assume the algorithm there have some state, then there's new information coming, then based on that we make a next decision. So I think that perspective is always from the MDP perspective. So the state capture everything in the past. But I was wondering, in the practice, is that useful actually to use all the previous image you are collecting? And because it may give you more information other than just a new image, right?
Yeah, so our state has always been this belief type state on the actual parameter that we're interested. So for example, if I'm tracking you, I'm interested in the angle of arrival and your channel coefficients. So the state is my state. And the information I have, so you're right. If it's not, we do update it. That update rule itself can be learned, right? To learn the memory of the process. Is that what you're saying?
Yeah, the reason I ask is it seems very successful, in empirical study, in reinforcement learning, people use the replay buffer. They just utilize all the previous data, randomly sample, then update the policy.
Yeah.
But modeling from MDP perspective, that's also always I come from, where you've got all the past data.
No,
just remember state and current data.
That's not true. If your model is not first order Markov, you don't want to forget the past data, right? So even in the theory, you know that you have to hold you have to use the memory how to update. So you can sort of say, I'm not going to do a Bayesian update without knowing that these things are correlated in time, rather than, they have. And so now, that's what I was saying. You can say, instead of writing the Bayes rule from the model memory, I can then ask myself, what is the rule that goes from prior to posterior?
But that's often a very complicated rule, right?
Not more complicated than having a playback, right? so the question is what is the sort of update of images that you have to play back the future, right?
Yeah, that's also related to Vijay's question. So I said, if something is moving, then if you look at the sequence of pictures, you may be able to figure out the physics of that.
Exactly. Yeah. So there, again, we do the same thing. It's Kalman-like. You have some predictable motion that you're going to feed forward, and then you have some random variations that you're hopeless. So again, the same question is, what part is that predictable part, and how much time you're going to feed it forward? Yeah, so that's a really, but it's not, I would argue it's easier than if you were just collecting all information kind of with an empty head and try to build a neural net for all of it. Because then, now I'm going to learn models that off of this wall are different than the metal wall, and I don't know which features, as Kamal was saying, which features are doing the sort of disambiguation of, where things are.
Thanks.
Sure.
This is a more general question. We see a trend these days that, every problem you have, you can throw in a machine learning algorithm and then you try to solve it. However, what I see in your work and what I really admire about your work is so much the special expertise that you put, not as a machine, you put the expertise from stochastic control or from decentralized control in addition to or informing the machine learning algorithm that you might use. So can you comment about the value of this special expertise that as educators or as researchers we need to instill to our students so that they don't see every problem as a machine learning problem?
Yeah. So the best example I have was a master's student of mine was working on imitation flight. So let's say I am a good pilot and I fly the drone in this room without hitting anything. And I fly it such that it can survey the areas I care, like let's say my bedroom, and now I have this drone, I go away, I'm traveling, and my alarm goes on. So I want my drone to just do exactly the flight that I did before. So it wants to just imitate me. Right? So it's a simple problem. So now it turns out, and you can do this with machine learning, it's a reinforcement learning. You can do silly things, you can just try to do exactly those actions. These drones have a lot of perturbation, so you can just say, I memorize the commands and just repeat. That won't work. So people have tried to use imaging techniques like SLAM, like localization mapping, to do this, to do that. They all require many, many rounds of data for every single room that you fly this. So I told my student, can we learn a model that is invariant to the room? And I said, let's think about how LQG solves this problem, right? So in LQG, you almost never talk about the trajectory x hat, x bar, or whatever we call it. Like there is x1 of t, that's the reference path, and you subtract it from all of your measurements. It's a linear system, so it goes out, and you will just look at putting your error x0 to be 0. So I told him, so that means that I need to know the reference path, and I have to compare it. So of course, in linear systems, you subtract. But if it's nonlinear, I can't really subtract. So then we looked at a neural net with two images. One image is the reference path that I have flown. One image is the variation that it's seeing online. And then you try to learn a neural net that corrects for this difference. And surprisingly, that neural net is very robust to which room you are. So that gave us this really nice. It can fly in any new room. I mean, and any is exaggeration, but it doesn't have the problem that Ming-Yan said, that you don't need to be the exact room to imitate. Now I take that neural net and take it to a new room, and I fly one time, and a SLAM will take like 7 or 8 times before it builds a 3D model at very high computation. So there are always these kind of examples where thinking about what the theory or caricature model will do really helps you to just sort of think about differently than what normally people do. Now, how do I advertise this to my students? I guess we just have to write good papers and send them to IROS and others. And I guess that's my motivation to build some of these, because it's hard to convince practitioners that there is value in thinking about these theoretical questions.
Contributions of non-AI to AI problems.
Yeah, exactly. And these days, it's filled with non-AI people making contributions there. So that.
Well, I think with that, let's thank the speaker again, and I'm going to present a award.